In this lecture, we'll define a very important concept in probability theory, namely independence, and what we mean by independent random variables. So the definition of independence between random variables is based on the definition of independence of events. So let's go back and remind ourselves of what we mean by two events being independent. Say that this is my sample space, S. Events are subsets of S. So let's say that I have an event A and I have an event B. This event here is the intersection of A and B. Let's say that the probability of event A is 0.5. The probability of event B is 0.6. And the probability of the intersection is 0.3. If this is the case, then we say that A and B are independent. They are independent because the product of P of A and P of B, 0.5 times 0.6, is equal to 0.3, which is the probability of the intersection. The general definition is then that A and B are independent events if P of A intersecting B is precisely equal to the product of P of A and P of B. So based on that, let's move on to random variables. So X and Y are now two random variables. The set X less than equal to A, that is an event. It's the collection of all outcome that the random variable X will map to a number that's less than equal to A, independent of what Y does. Similarly, Y less than equal to B is an event as well. Let's call this event A, and this is the event B. The event A and the event B depend on which number I use for lowercase a and b. The intersection of A and B is then the event that X is less than equal to A and Y is less than equal to B. So by just using the definition we have for independent events, A and B are independent events if the probability of the intersection, the probability that X is less than equal to A, Y less than equal to B, is equal to the probability of A, the probability that X is less than equal to A, times the probability of B, Y less than equal to B. If this is the case, then these two events are independent. Well, we have a name for this probability. We call that the Joint Cdf. So that's f of A comma B. This is the marginal CDF of X evaluated at A, while this is the marginal CDF of Y evaluated at B. So we concluded that this event is independent of this event if this relationship holds. So we are now simply going to say that the random variables X and Y are independent if this relationship holds, no matter what the values of A and B are. If this relationship holds for all A and B, then these two events will always be independent events, and then we say that the random variables are independent. So let's summarize this. X and Y are two random variables. Doesn't make any difference if they're continuous, discrete, or whatever. We're going to call them independent random variables if this event, which we call uppercase A, and this event, which we call uppercase B, are independent events for all real numbers A and B. That is, no matter which number you put here for A and B, you must end up with two independent events. This is the probability of the intersection. That must be equal to the probability of the first event multiplied by the probability of the second event. And it must hold for all X and Y. So this is not too difficult to check. if I know the joint CDF, I can calculate the marginal CDFs and then just simply check if the product of the marginal CDFs is equal to the joint CDF. However, in probability theory, we tend to work more with probability mass functions for discrete random variables and probability density functions for continuous random variables. For example, if I have two continuous random variables, then simply by differentiating both sides, first with respect to x, then with respect to y, I will get on the left hand side f of x comma y, and on the right hand side I will get the marginal PDF of x multiplied by the marginal PDF of y. So an equivalent condition, if I have continuous random variables, is that the product of the marginal PDFs must be equal to the joint PDF. This result will hold even if both random variables are discrete random variables. But in that case, obviously, this would be the joint probability mass function, and that needs to be a product of the marginal probability mass functions. So let's summarize what we just said. If x and y are both discrete random variables, or if x and y are both continuous random variables, then the condition on the CDFs is equivalent to a condition on the PMFs in the discrete case and the PDFs in the continuous case. Here is a simple example for continuous random variables. So my joint PDF is 4xy. The range of x is 0 to 1. The range of y is 0 to 1. We can quite easily find the marginal PDFs. I get the marginal PDF of x by integrating away y, and I get the marginal PDF of y by integrating away x. Here we can clearly see that the joint is precisely equal to the product of the marginals. 2x times 2y is equal to 4xy for all x and y. So in this case, x and y will be independent random variables. Let's just talk a little bit about the case when we have more than two random variables. So let's say that we, instead of having two random variables, we have n random variables denoted by x1 through xn. In that case, we actually have two different definitions for independence. We can say that they are mutually independent, and we can say that they're pairwise independent. It all depends on the independence of events. So if these n events are mutually independent, then we say that the random variables are mutually independent. If the events are only pairwise independent, then we say that the random variables are pairwise independent. Remembering that a collection of n events may be pairwise independent even though they are not mutually independent. If you are told that a sequence of n random variables are independent without knowing whether they are mutually independent or pairwise independent, then the convention is that we mean that they are mutually independent. So the term independence by itself in most cases means mutually independent when we have a sequence of more than two random variables.